Hello, this is Logan Shipkin, and you're listening to the Fallible Animals podcast. Today I have one last interview from a few months ago, this time with scientist and science writer Lewis Dartnell. I had interviewed him for a magazine that was published in Quillette, the link to which I've included in the show notes page, along with the link to Dr. Dartnell's website. Professor Dartnell is a research scientist and author based in London. His research is in the field of astrobiology and the search for microbial life on Mars. He's also active in delivering live events at schools and science festivals, and he's appeared on numerous TV documentaries and radio shows. He's won several awards for science writing and outreach work, and he's published 4 books, his latest of which is much of the subject of today's conversation. It's called Origins: How the Earth Made Us, and it's already a Sunday Times bestseller. Lewis and I covered both his latest book and his scientific field of astrobiology. If you want to learn more about the possible origins of humanity, the development of civilization, and our search for extraterrestrial life, I highly recommend this interview. Again, I apologize for the poor audio quality, but this interview was conducted before I had bought a mic, and I promise that that's the last time you'll ever hear me say that. If you're enjoying this podcast, please consider sharing. My goal with this podcast is to provide bite-sized pieces of science and philosophy for people to enjoy and hopefully learn from. By now, we have a nice little library. Some episodes about critical rationalism, some episodes about constructor theory, and some interviews with interesting thinkers centered around fundamental ideas. And without further ado, I give you Lewis Dartnell. Okay, great. So first we'll talk a little bit about your new book, Origins, which I recently finished. Early in the book, you described this hypothesis that I had never heard before, which causally links basically the cosmic cycles of the Earth with the evolution of human intelligence. So could you please just describe to me this hypothesis and just how new is this hypothesis and what is the evidence to support it?
Yeah, so one of the big questions in human evolutionary biology is what drove our evolution from being tree-swinging apes, highly intelligent hominins that then went on to build civilization and kind of inherit the world. And primarily what needs to happen is the land around you needs to dry out. The forests need to be replaced by grasslands, by savanna. And what was driving that process over 5-6 million years since we diverged from the chimpanzee lineage was East Africa dried out because it was being pushed upwards. So the Ethiopian highlands were rising, probably because of a magma plume beneath the crust of the planet was rising up from the interior. And that also then drove this splitting of the crust itself in a characteristic Y-shaped fracture, with 2 of those arms being the Red Sea and the Gulf of Aden, which then flooded in with the sea. And the third arm of this is the Great East African Rift Valley, and that serves to block the moisture-rich air from either the ocean or from the rainforest in the interior of Africa from blowing over to East Africa, and so it's dried out a lot. And so that what should be rainforest in East Africa has now dried out and is savanna, is grassland. But the bigger question, what's been puzzling paleontologists for a while, is what was it specifically about the Rift Valley in East Africa, this feature of plate tectonics that created us as such an exquisitely intelligent species of ape. And the answer that's been emerging over recent years is that the particular landscape of the Rift Valley, where it's got the contrast between these high mountainous ridges, the shoulders on either side of the rift, and the very low down valley floor, which is very hot and very dry, means that there are lakes in that Rift Valley that are very, very sensitive to the precise balance between precipitation and evaporation, i.e. how much rain there is and how quickly it evaporates back away again. And that tectonic landscape interacts with the Milankovitch cycles, with these cycles, cosmic cycles in Earth's orbit or the tilt of the planet, which vary slightly the amount of rain that the tropics experience. So there is this whole set, this string of lakes on the Rift Valley floor that in certain periods of time, for certain periods, flicker rapidly in and out like a loose light bulb, and so create a very unstable climate, a very rapidly fluctuating climate. And so the idea is that it is that rapidly changing environment, that rapidly changing climate, that we had to evolve intelligence to be able to survive in, rather than any other adaptation of other animals.
And does this hypothesis have a name?
The lakes have been called Amplifier Lakes.
Mm-hmm.
And I give references in the book, if you've got hold of that for yourself now, to people like Mark Maslin and other researchers who've been doing, the actual research into this, and I've been writing up their theories in that particular chapter of this book. But the Amplifier Lakes is the name given to those lakes which are very sensitive to those climate fluctuations.
Right, yeah, I remember that in the book. It's such an interesting idea. I'm surprised it's not more commonly known in the common consciousness, popular consciousness.
Well, I think the answer is it's a relatively recent development. It's a relatively recent theory or explanation to come up. So I think people are generally aware that East Africa has dried out and forest became savanna, became grassland, and that's what drove our evolution from chimpanzee-like apes into bipedal, naked-like hominins. But I think you're right. I think people aren't generally already aware of the Amplifier Lakes and what was specifically unique about the Great Rift Valley and these Milankovitch cycles.
Yeah, to me, this really colors in a lot of the details, because I think you're right. Most people understand East Africa, that's where we evolved, etc. But the Amplifier Lakes, to me, is very interesting, and hopefully it becomes more popular should it continue to be corroborated and so forth.
Exactly, yeah, exactly that.
Cool. All right, so moving on, you argue in the book that basically the aimless wandering of the continents into their current configuration via plate tectonic dynamics indirectly basically gave the Eurasian civilizations a big advantage in terms of maturing over time compared with non-Eurasian civilizations. So if you could maybe give a brief overview of how did Earth's geography at the dawn of civilization advantage these Eurasian civilizations compared with those that aren't Eurasian, and also maybe if you want to talk about how the distribution of plants and animals also gave Eurasian civilizations a big advantage.
Yeah, so this is similar to the sort of stuff that Jared Diamond covered in Guns, Germs, Steel. And he was looking specifically at Eurasia versus the Americas. And there are other arguments as to why Africa never developed a civilization that became dominant in the way that European civilizations did, or ditto with Australasia. But talking about just Eurasia and the Americas, when the supercontinent Pangaea broke up during the last great kind of supercontinent cycle, it just so happened that one big chunk of it, Eurasia, then had Africa riding north and India riding north to collide back into it. So you get this east-west orientated huge landmass, whereas the Americas, which were ripped off by different tectonic faulting processes and seafloor spreading centers, the Americas got pulled away from Pangaea as it was disassembled into a predominantly north-south orientated continent. And one of the main differences that gives you for agricultural communities or agricultural civilizations is that it is relatively easy to move domesticated crop species along the same line of latitude, i.e. east-west, because you have generally the same seasonality, length of day, that sort of thing which is important botanically, important to plants. So that meant that across Eurasia, plant species of things like cotton or rice or wheat could be moved relatively easily across all civilizations and all cultures across the continent, whereas in the Americas, which is north-south, it was much harder, it was much slower to move crops around. So one of the reasons why American societies were biologically disadvantaged is it was harder for them to move their crops between different locations. And there's another quirk of that distinction between Eurasia and Americas was that the Americas were impoverished in the selection of large mammal species that they had that could be domesticated, whereas Eurasia had a lot more. And part of that was the reason is that it was actually the first Americans or the first humans to migrate to America across the Bering Land Bridge, probably triggered the megafauna extinction. So that the extinction, the disappearance of many of these large animal species was probably driven by the first appearance of humans in the Americas in the first place, which again is something I talk about in the book. So that there was both plant reasons and animal reasons why the Americas were biologically held back as a broad brushstroke grand theme of history.
I did think of Guns, Germs, and Steel when you were talking about that stuff. So
yeah.
It's
a very interesting book.
It is. But I think... sorry to interrupt.
Oh, so I was just saying that I was delighted when some of the newspaper reviews in the UK compared Origins to Jared Diamond, Guns, Germs, Steel, and Sapiens by Yuval Noah Harari.
Mm-hmm.
That was that sort of book that I was trying to write.
Yes, certainly Origins reminded me of Guns, Germs, and Steel in the sense that you both peel back causal layers in a coherent way, which I think is a very fun way to... Because I think of the story of humanity so far is kind of like a really awesome fiction story, but it's not fiction. And so, you know what I mean? A good story has a lot of causal events and so forth. Anyway, that's just an aside. So...
No, I think you're right. The narrative of the human race.
Yeah,
exactly. What frustrated me about Guns, Germs, Steel is that it was a great book. It was a very interesting read. It won a Pulitzer Prize deservedly. But it frustrated me because it only looked at a very few number of these deep causal links. Mm-hmm. And what I wanted to explore in Origins was I thought there were a large number of more links and these other kind of chains of causation that could be used to explore the whole of human history. And that's what I tried to research and then write for this book.
Yeah, no, absolutely. I mean, I read Guns, Germs, and Steel a few years ago, but I don't recall him linking the cosmic cycles like you did, which is why I opened the interview asking about that. That seems roughly original.
Yeah, and there's a lot of stuff that hasn't really been talked about that I couldn't see about the influence of the oceans and the age of exploration and building these transcontinental trade links and the beginnings of globalization.
Right, yeah. Towards the end of your book, that is. So moving on to the differences between different civilizations in the world, you also write about a lot of the frictions between settled civilizations and nomadic peoples throughout history. So how is it that we have these two vastly different lifestyles emerge in the same species, and why is it that sometimes they would clash very violently?
Yes, this comes down to one of the fundamental contrasts within the Eurasian continent, within the Eurasian landmass again. You have these different climate bands that are layered from the equator to the poles of planet Earth. And the important ones for this part of the story were essentially the temperate climate band, where it is mild enough and moist enough, rainy enough, that you can support agriculture to grow enough food for agrarian societies, and therefore cities and therefore civilizations, settled civilizations built on growing crops in the ground. And further to the north, you have a great stripe of a climate band across the very backbone of Eurasia, which are the steppes, so the grasslands of Eurasia, which are the same as the grasslands of the prairies in North America, and then you have a mirror image stripe in the southern hemisphere as well. And the steppes are much more arid, which means you cannot effectively grow enough food for yourself by using agriculture, but it does support very well an alternative mode of life, which is nomadic pastoralism, i.e. herding huge numbers of goats or sheep or cattle, eating the grass, which humans cannot eat themselves, and therefore essentially using those herbivorous animals, those ungulates, almost like a processing machine to turn inedible grass into meat or milk or other animal products which humans can digest and can eat. But that leads you into two very fundamentally different and antagonistic lifestyles. And repeatedly throughout Eurasian history, so going right back to the Bronze Age through to the sort of 1700s, so for thousands of years, there's a grand theme of Eurasian history where periodically, and probably driven by climate change, regional climate change within the steppes, these nomadic horse-riding peoples are driven out of their homeland to hassle or raid or invade these settled civilizations around the rim of Eurasia. And this is very familiar from classical history of the Huns appearing out of the steppes and collapsing, leading to the collapse of the Western Roman Empire. It happened again with the Mongols appearing, thundering out of the steppes and building the largest land empire the world has ever seen by unifying the lands across the steppes. And when you look at it in this light, the Great Wall of China, so that the Chinese have been repeatedly hassled by what they would refer to as barbarians, horse riders coming out of the steppes, and they therefore built the Great Wall of China as a defensive barrier. But when you look at it in this context of planetary science interacting with history, the Great Wall of China effectively just follows this boundary, this line between two different ecological systems, between the temperate zone where you can grow crops and the steppes and the grasslands where you have to be nomadic and herd sheep and ride horses.
That was very interesting to me. And I think you used that line in the book where you describe the animals as sort of conversion machines. I thought that was very...
Yeah. I liked thinking about it in that way.
That's a very physics-y oriented way of thinking about it, which I appreciated. Yeah. So that was good. Okay.
You're a physicist yourself, are you, Logan?
I have a undergrad degree in physics, and now I am getting a PhD in evolutionary theory.
Oh, I see, yeah.
Yeah.
Very interdisciplinary as well.
You're right, exactly. So I saw you were talking about how astrobiology is interdisciplinary, which is cool. And that basically this is an aside, I think I read on your page maybe how to get into astrobiology. You basically said you can come from anywhere, which I think we need to emphasize that more just in the culture, that there's no such thing as, okay, you need to get a degree in this before going into that. I mean, it's all, because reality is coherent.
I think you're absolutely right.
Yeah.
And I think asking a professor what career route they took to be where they are is almost, by definition, the worst question, because 20 years later, those same career paths probably don't exist anymore.
Right,
and
exactly.
So, to a large extent, everyone needs to find their own path from where they are now to where they want to be in 10, 15 years' time.
Yeah, exactly. Okay, so last question about your book, which follows from the previous. Implicit in your book, is there an argument for a kind of ecological determinism, such that if one were to look at Earth now, could one say with relative certainty, okay, the great human civilizations will emerge, let's say where they do, and that nomadic peoples will emerge where they have? Or do you think there's much more randomness than that?
So I think you need to be very careful to hint or imply things like geographical determinism. And in the past, historically, arguments within geographical determinism have been used as excuses or to justify, territorial expansionism before the Second World War, or racism and colonialism and slavery before that. So the idea that one peoples is intrinsically or naturally linked to one part of the world, to a particular territory or particular location, I think is not what I'm talking about. Nor am I talking about that some peoples are inherently better or brighter or progress or advance more quickly than others. But what I am talking about is that you don't want to throw the baby out with the bathwater. And undeniably, there is a deep link between physical, geographical features of the planet, or to do with the atmosphere or the ocean, and what opportunities or challenges that's given people through the ages. And so for some of the things we've been talking about, to do with like the climate bands of Eurasia, those would be there even if you reround history back to 100,000 BC, 10,000 BC, and push the play button again. Those physical features of the planet would be the same, and they would therefore have a similar driver or influence or effect on the subsequent development of, in this example, nomadic societies or settled civilizations. The pattern of winds around the world, driven by atmospheric circulation and dynamics, they would be exactly the same. So you would be able to have trade routes along similar lines, simply because of the physics of the atmosphere. So I think if you look in a broad enough brushstrokes, both in terms of historical time and planetary scale, as in looking over big enough regions, big enough areas, you can be fairly confident about predictions about how that would affect the human story. But you can't start predicting particular things or saying that a particular war or a particular leader came about because of geographical features.
Right, and in fact, your answer, it's kind of an argument against genetic determinism, no? Because it says that if you were to, let's say, take our ancestors in East Africa and shuffle them around such that those people who end up in Eurasia are different than those who end up in, let's say, North America, I'm just picking places, that you would roughly get similar lifestyles even if the genetics are different.
So, I mean, this is the point, that the genetics across the entire human race that migrated out of Africa are basically identical. And I give the fact in the book: there is more genetic diversity between two troops of monkeys on opposite sides of a river in Central Africa, or check the fact in the book, than there is in 6 billion people living across the world outside Africa. There is more genetic diversity within native African peoples. So in that sense, it's not genetic reasons why Eurasian civilizations were technologically more advanced than American civilizations in the early 1500s. It's not genetics. We are the same people, the same species, and it was more these geological and geographical influences that were important in that sense.
Okay, so let's move on to astrobiology, if that's all right with you.
Yeah, of course.
Okay. Astrobiology is the quest, which I'm sure you know, to understand the origin, evolution, distribution, and future of life in the universe. Since you've begun your research career as an astrobiologist, which I think was around 12 years ago or so, in which of these subfields, origin, evolution, distribution, etc., have scientists made the most progress, and what exactly have we learned in that subfield?
Yeah, so astrobiology is a very interdisciplinary field of science, as we were just saying earlier. So I've got friends within astrobiology. So I came from the biology background, but I have friends that come from geology and planetary science, or chemistry and biochemistry, microbiology, physics, astronomy, engineering and robotics, or instrument design. It really is, astrobiology as a discipline really is the thin sliver of overlap right in the middle of a huge Venn diagram of different disciplines, different fields. And over the last 15, 20 years, we've been making huge advances in basically all of those fields. And so you might pick out things like extremophiles and our realization that life on Earth is, in fact, incredibly adaptable and tolerant of a huge range of different hostile environments, and therefore places like Mars are habitable in that sense. Or we've been discovering solar systems beyond our own star, beyond our own sun, and we are finding more and more Earth-like extrasolar planets. So there's been huge advances in that field as well. Or in our capability with robotics and instrumentation and exploring planets like Mars by sending our robotic emissaries, our robotic explorers, to do what humans are not able to do just yet. So there's been big advances in those areas, as well as many others within astrobiology, that have been giving us this increasing optimism that we are on the verge of discovering life on other planets if it's there. But it is our generation that could make that fundamental, profound discovery.
Okay, so basically it's right. Everything is sort of interconnected, and that we might be on the verge of something. Very cool. So you hinted at this a little bit, but what has recent research taught us about what features, in principle, we should expect life to have when or if we discover it elsewhere?
So within astrobiology, you try to base your expectations and your experiments and your instruments on what is already known. So we base it on what we know of terrestrial biology and what sort of chemistries can enable something as complicated and complex as even a single-celled organism. But you also want to not be blinkered. You also want to keep an open mind about how life could be different from our example. If life is extraterrestrial and alien, by definition, it could be different from us. So you're trying to play off those two thoughts against each other. So when we go looking for life on Mars, for example, we're not looking for a particular molecule. We're not looking for DNA itself. We would look for complex organic chemistry in general, the sort of chemistry that you would not expect to have arisen, the sort of molecules that would not have been synthesized by geochemistry or by astrochemistry, but only by biochemistry, by the organization and direction that an organism can muster. So in broad brushstrokes, we look for organic-based chemistry, carbon-based chemistry, and water-based life. Although possibly on somewhere like Titan, we should relax that life would be water-based. It might be methane-based or ammonia-based. There might be other solvents for life, other wet stuff that biochemistry and cells could be built on, but probably using carbon chemistry, that life, wherever we find it, will probably be organic.
And do you expect there to be an information code wherever we find life?
Yeah, so the three things that life does, and therefore you could use to start building a definition for what you mean by life, would be some kind of complicated chemical network to extract energy from the environment and to synthesize the building blocks, the Lego bricks of new cells. So you would need some kind of biochemistry, some kind of metabolic network. You would also need some kind of information storage, retrieval, and transmission system. So we use DNA for that, and for our genetics in terrestrial life, and RNA. And you would then need some kind of membrane, some kind of bag or a sac around your cell to simply delineate yourself from the environment. So you can control your internal conditions, so you can make sure that your biochemistry isn't diluted and washed away in the entire ocean. So those are three things that all cells on Earth have. And you can therefore start making expectations about what chemistry or molecules those three things might be built out of. But life is a process, life is a function, not an object, if you think about it that way.
Yeah, I agree, which is one of the limitations of language, I guess. If we called life, quote unquote, living, it might be easier, but anyway.
Exactly, and then you might have problems with how you could detect dormant life or signs of stuff that has once been alive but is now dead. Could you find biosignatures of extinct life on Mars? Like, what fingerprints does life leave behind even when it's no longer active?
Right. All right, so I want to ask you about something that I had never heard of called the Shadow Biosphere. And what could the Shadow Biosphere teach us about the possibility of life in the universe?
Well, we know that all life we've discovered so far on Earth is related. We can all be put as twigs onto the same huge evolutionary tree, the same phylogenetic tree. And at the root of that, there is a progenitor, a last universal common ancestor. But the fact that all life we've discovered on Earth can be traced to the same Luca does not mean that life only evolved once on Earth. It just means that we are all the survivors of the same origin. And it stands to reason that if the conditions on Earth were appropriate for chemistry to become biochemistry, to become organisms, to become life, that wouldn't have happened in just one location. It would have happened in several locations, multiple locations. And perhaps it's not true that our form of life outcompeted all other forms. Perhaps there are locations on Earth where we were not able to colonize as effectively, where the descendants of some other origin of life on Earth remain even today. So perhaps extreme environments where our form of biochemistry falls apart. So maybe very high temperatures, maybe in the depths of a hydrothermal vent, maybe deep in the Earth's crust. These are the sort of places we might expect to find what has come to be known as a shadow biosphere. Life that is, in some senses, alien, even though it was born and lives on the same planet as we do. It is life that is based on a fundamentally different biochemistry because it came from a different origin event, a different genesis. The problem with that, though, is how do you find something which is different from what you are familiar with what you recognize? So in that sense, it's a very similar question or similar problem to astrobiology and looking for life on Mars, looking for other Earthlings, but Earthlings with a very different biochemistry on our own planet.
Yeah, that's a very exciting idea. That would be fun to find almost a cousin tree of life.
Exactly. It'd be a second tree. It'd be the second example of a forest on planet Earth.
Right.
And maybe there's not just one other shadow biosphere. Maybe there's many. But I mean, you start having difficulties in explaining how that situation would be stable. You would expect, even if they're based on different biochemistries, for one to start outcompeting the other. In the same way that if you have many species living in the same niche on Earth, they start outcompeting each other and only one prevails. So there might be one other shadow biosphere, but it's hard to understand how lots of different shadow biospheres would be a stable system and not outcompete each other.
Well, maybe it could be stable in the same sense that we have multiple species now, so that it's just a level up, well, many levels up.
But the difference in those two situations is species being created anew all the time. You have divergence events, you have a new species coming about, you might have a mass extinction like 66 million years ago, and species are able to colonize into now vacant niches and have another evolutionary adaptive radiation, another divergence. The problem with an origin of life is when you're first getting started, you are very, very primitive, and you'll get gobbled up immediately by an established organism, by a cell. So if there was multiple origins of life on Earth, they would have to have happened within a short time frame, geologically speaking, before any one of those could start diverging and spreading around the world, and therefore eating any tasty organic molecules lying around. So once you've got one origin of life that has spread around the world, it basically closes the door on any further origins of life from primitive, simple biochemistry. Because an origin of, like Darwin's pond, an origin of life lying around, all you're describing now is just a tasty soup for a cell that encounters it.
Right. That makes sense. So what recent steps have scientists taken to look for life both in the solar system and beyond the solar system?
Well, so we're designing probes to launch particularly to Mars, and next year, 2020, both NASA and the European Space Agency, ESA, are sending their own rovers to look for signs of life on Mars, and that's NASA's Mars 2020 and ESA's Exomars rover. Exomars is particularly interesting because it will have a 2-meter long drill on board, so we'll be able to get underground on Mars and then pull handfuls of that Martian dirt back up to the surface from where they've been protected underground, and then analyze them for signs of organic molecules and hopefully even biosignatures, signs of life itself, whether that's extinct or extant. There's plans on the drawing board for missions out to Europa, which is considered to be another habitable zone, another potential site of extraterrestrial life in our solar system. And then with the extrasolar planets outside our solar system and across the galaxy as a whole, we're building steadily more capable space telescopes and ground-based observatories that can not only detect that a planet is there around another star, but actually start characterizing that planet for us. And so we would start looking for planets in what are known as the habitable zone or the Goldilocks zone around their star. We would then start doing infrared spectroscopy on the light from the planet and start looking for the telltale signature, the telltale fingerprint in that spectrum of gases like oxygen and methane, which in combination would be a very, very indicative biosignature. That it would be very strongly suggesting that there is life, and specifically photosynthetic life, on that Earth-like planet orbiting another star.
Wow, that is very exciting indeed. So that overlaps a little bit with my last question, but feel free to give me any information that you want to, that you haven't already. So what are the most exciting astrobiology research projects that are going on in 2019, whether or not you're involved in them?
Yeah, so the most exciting space missions are launching next year on Exomars and Mars 2020, and those I'm very, very excited about. And it'd be good to look into the future a bit more with ESA's JUICE mission, Jupiter Icy Moons Explorer, which will hopefully give us a lot more information about Europa, and then the possibility of a dedicated Europa probe being sent out there. So if you're looking towards the horizon, those are the most exciting upcoming space missions.
And are you involved in those or no?
So I'm loosely involved in the Exomars Probe because it's a European probe. I'm working with people on the instrument teams, the science teams for that. The sort of research I do is into extremophiles and biosignatures that could be detected by the instruments on board Exomars. To be clear, I'm not like a mission scientist. I'm not one of the designers of the probe, but the work that I do is very closely linked to the sort of things that are important for Exomars.
All right, Lewis. Well, thank you very much. You answered all my questions. Is there anything else regarding your book Origins or even your previous books or astrobiology that you think is important for the reader to know that I didn't ask about?
No, I think your questions are very interesting. You've had a good selection of them. And thanks for the call. Thanks for getting in touch.
Thank you very much, Lewis. Yeah, it's been a lot of fun.
All right. Cheers, Logan.
All right,
Take care of yourself.
Bye.
Bye-bye.